3.8 kilometers below the surface of the Atlantic, the physical remains of the RMS Titanic lie submerged in total darkness, broken into two separate pieces, resting 600 meters apart on the ocean floor. This wreckage represents a striking paradox. We are looking at a massive vessel equipped with redundant safety systems, specifically engineered to be impossible to sink, yet it catastrophically failed in less than 3 hours. Looking at the pristine structural profile of the ship before its maiden voyage, the mathematical models of its buoyancy, and the physical thickness of its steel suggested total invulnerability to the hazards of the ocean. To understand why this occurred, we have to look past the hull's interaction with the ice. The disaster represents a system failure, where a cascade of operational decisions bypassed the physical safety architecture. To understand how the most advanced maritime safety system of 1912 collapsed, we have to forensically work backward, from the structural design of the hull to the precise kinematics of the collision, down to the specific protocol failures that sealed its fate. The confidence in the Titanic's classification as an unsinkable vessel was grounded in very specific structural logic. The first major physical safeguard was a heavily reinforced double-bottom hull. This was engineered to protect the ship against vertical grounding on the ocean floor, ensuring that if the bottom scraped a reef, a second intact layer of steel remained above it. While the underside was practically impenetrable, the lateral sides of the ship relied on only a single layer of steel. To compensate for this, the architects installed transverse bulkheads, dividing the length of the hull into 16 separate watertight compartments. The ship's buoyancy model established a critical engineering threshold. It could sustain massive damage and remain entirely afloat with a maximum of 4 flooded compartments. The mathematical failure point was absolute. Inundating 5 or more compartments would compromise the entire buoyancy system and inevitably pull the ship under. These physical safeguards were designed to mitigate localized, head-on collisions, where the damage is confined to a small impact zone. The entire architectural confidence of the Titanic relied on a flawed geometric assumption. The builders calculated that a longitudinal, side-grazing impact spanning multiple compartments was a statistical impossibility. There is a persistent myth that the iceberg sliced through the ship's hull like a sharp knife. That is not how naval-grade steel reacts to ice. The true mechanism of the breach was a product of kinetic energy, mass, and blunt material deformation. On the night of April 14th, the forces involved were staggering. A 1.5 million-ton iceberg intersected with a massive steel structure traveling at 21.5 knots, or roughly 40 kilometers per hour. The initial violent impact occurred precisely at the ship's bow, on the front right side of the hull. But the collision did not stop at the bow. Rather than a localized head-on crash, the failure mode was an extended, grinding impact that lasted a full 10 seconds. The massive weight of the iceberg dragged directly along the ship's single-layer side, the exact geometric point left unprotected by the double-bottom hull. This sustained blunt trauma didn't open a massive gash. The immense pressure simply popped the steel rivets and created a series of microfractures and small holes along the metal plates. Because the scrape dragged longitudinally down the ship, it completely bypassed the logic of the transverse bulkheads, opening seams across 6 distinct watertight compartments simultaneously. The fatal math was set. By breaching 6 compartments in a mere 10 seconds, the impact blew past the absolute 4-compartment limit. Total loss was now a mathematical certainty. We have to ask how the largest ship in the world found itself moving at top speed into a dense ice field, especially after the radio operators had received 7 distinct ice warnings that very day. The answer lies in the overriding commercial pressure applied directly from the top. Joseph Bruce Ismay, the chairman and managing director of the White Star Line, was aboard the ship. Company leadership actively suppressed the incoming ice warnings. Their objective was to maintain maximum speed across the Atlantic to secure a headline-grabbing 6-day crossing record. This demand for speed collided with severe environmental variables. The ocean was completely calm, meaning there were no waves breaking against the icebergs to give them away. There was no moonlight, temperatures were plunging, and visibility for the lookouts in the crow's nest was near zero. This drastically compressed the reaction time, leading to the final operational failure, a panicked steering maneuver at exactly 11:39 p.m. Upon finally spotting the massive iceberg dead ahead, the steersman, Robert Hitchens, misunderstood the deck officer's instruction. In the ensuing panic, he turned the wheel to the right, steering the vessel directly into the collision path instead of turning away. The ship's longitudinal blind spot was only exposed because a commercial demand for speed and a human moment of panic overrode the available environmental data. Once the collision occurred, a secondary cascade of failures began, exposing a catastrophic breakdown in emergency protocols during the evacuation. This chart details the stark math of the evacuation setup. We see an onboard population of roughly 2,200 people, but a total lifeboat capacity of just 1,200. Because the passengers were continually told the ship was unsinkable, initial complacency resulted in a drastically low utilization rate. The very first lifeboat lowered had a capacity for 65 people, but launched with only 28 seats filled. The fundamental scarcity of these lifeboats was a deliberate design choice. The manufacturing company viewed additional boats as unnecessary visual clutter that would crowd the deck of an unsinkable vessel. This arrogance extended to procedural negligence. The captain actually canceled the scheduled passenger safety drills on the exact day the collision occurred. The situation was compounded by a catastrophic external communication breakdown. The SS Californian was positioned just 37 kilometers away, close enough to be seen on the horizon. But the crew had halted the ship for the night, powered down their radio equipment, and misinterpreted the distress flares lighting up the sky over the Titanic. The most advanced structural hardware in the world is entirely useless without rigorously enforced operational protocols. The lack of basic evacuation training and radio discipline sealed the fate of the passengers left on board. By 2:20 a.m., the mechanical timeline reached its violent conclusion. Thousands of tons of water filling the forward compartments shifted the center of gravity, dragging the bow underwater and forcing the massive stern high into the air. The unsupported structural stress exceeded the hull's tensile strength, snapping the ship in two before it plunged. The immediate legacy of this disaster forced a total, systemic rewrite of global maritime safety regulations. By 1914, the International Ice Patrol was established to rigorously monitor and track environmental threats across the Atlantic routes. Soon after, the International Convention for the Safety of Life at Sea, or SOLAS, was signed. It permanently mandated strict operational rules, including continuous 24-hour radio watches on all passenger ships and sufficient lifeboat capacity for every single person on board. The Titanic demonstrates that engineering safeguards are only as effective as the protocols governing them. If speed and profit are permitted to override safety data, even the most advanced systems will eventually fail.